Okay, recording is started. Hi, everyone. Thank you so much for having me, and thanks for being here. My name is Jacob Tony. I am a now fourth-year PhD student in chemical engineering and computational science, working at MIT in the Kulik Group. And today I'll be telling you about some of my recent work on applying machine learning to transition metal chemistry for the discovery and the design of functional catalysts and materials. So I'll start off with a background, of course, just setting the stage a little bit and motivating the problem. I'll move on to talking about a previous publication from last year on graph neural networks for predicting metal-ligand coordination, which is just how does a transition metal bind to organic molecules, which we refer to as ligands. Then I'll move on to relaxing some assumptions that we made in the initial work, where we leveraged some ensemble learning to study dynamic coordination modes, like how does this bonding change over the course of a reaction. I'll close with a little bit of extensions to generative models, just one slide or two on this where we discuss applying these models in different contexts in more recent work. And then finally, some discussion where we'll do Q&A and I'll answer some questions. So getting started. So transition metal complexes are very practically and scientifically relevant systems. They see very broad applications in catalysis, photochemistry, and biology, largely due to the unique electronic structure of d electrons. And the availability of, ligands to come into the metal and change the electronic properties. Biology, they're relevant not just in transition metal drugs, but the overwhelming majority of enzyme active sites, which do these dream reactions that we're interested in, are catalyzed by transition metals. But if we look at the concentration of these different transition metals in the Earth's crust, we see that our best homogeneous catalysts, like the Schrock or Wilkinson's catalyst, our favorite metallodrugs like cisplatin, and most of our OLED or photochemical emitting devices are all based on these fleetingly rare metals like iridium, rhodium, platinum, palladium, and so forth. But nature somehow, over the course of around 4 billion years, has figured out how to do similar, if not more complex chemistry with metals like iron, zinc, and nickel. So the idea is that some design space exists for sustainable transition metal catalysis, where we can hopefully stop using these more rare earth metals and things that are environmentally damaging to mine, and start using chemistry that's just more easily accessible around the Earth. One example that I'd like to start with to motivate this is Suzuki coupling. It's a classic catalytic reaction for carbon-carbon bond formation used in the production of various fine chemicals and fuels at ambient conditions. And it's driven by a palladium, some complex of palladium and a ligand. However, the knowledge of how that palladium and ligand come together to form this precatalyst is not straightforward to determine. There's some in situ complexation that occurs when you add your palladium salt and when you add your ligand into a solution. This coordination mode is not well known unless you do time-consuming and expensive experimental characterization of the complex. And this coordination mode can also be dynamic. So active sites can open up, a substrate can come in, it can undergo the catalytic transformation, the substrate can dissociate, but knowing what the actual complex that's in this solution that's driving the reaction is not straightforward to determine. So I'll talk a little bit more about why that matters in the next slide. So a lot of the unique properties of a transition metal complex are attributable to their metal-ligand coordination. These complex structure property relationships are functions, of course, of the metal. So I'm showing you manganese 3 here, which could be a singlet or a triplet or a quintet. But in general, the identity of the metal, the oxidation of the metal, and the spin, which is related to how the electrons are paired up, if they're all paired, if some of them are unpaired, and so forth, dramatically changes the electronic properties. You also, of course, care about the ligands, which are these organic molecules that bind in some fashion to the metal. On the left here is aniline. It's pretty straightforward to look at this and say, yes, I think the nitrogen is going to bond to the metal. The middle here is acetylacetonate. It's a little bit more complicated, but you can tell that it's going to be the 2 oxygens. And on the right here, I had to write down the name. It's 5-bromo-2,2-oxyphenylamino-methylphenolate, which a big molecule, but don't have the name for you. It's still relatively straightforward to look at this and say, yeah, it's probably going to be these 3 that will bind to the metal, which is resulting in the complex you see here on the left. However, and now I have circled the coordinating atoms as spheres. However, this metal-ligand coordination, while straightforward to determine manually for like toy ligands, when we're looking at vast chemical spaces and vast chemical libraries to try and design these complexes that do the challenging chemistry we want, you end up with things like this, which I don't even know the name of, and I couldn't find it in PubChem either. If you look at this ligand, do you think it's is it going to be bidentate? Are there going to be 2 atoms which bond to the metal? Maybe there'll be 3. And if there are 2, is it going to be which nitrogen, which oxygen? Maybe the sulfur is involved. And it's not straightforward to determine just from chemical heuristics or even from things like ligand field theory, or even looking at statistics of the whole data set, data sets of like ligands and how they bind to metals. So what we did is we took a deep learning driven approach to try and solve this problem. Because metal ligand coordination, despite being a necessary input for whatever computational method you have, a force field, a quantum mechanics calculation, or even a deep learning calculation, it's very challenging to determine a priori. Great. So now I'll move on to talk about the first publication of the day, which is a series of graph neural networks that we trained using these ligands as inputs to try and predict how they'll bind to the metal. So the first thing we did is we turned to the Cambridge Structural Database, which for those of you who aren't familiar is an open source online repository of crystal structures. So everything in there has been synthesized and crystallized, and the 3D coordinates of all the atoms deposited. We mined this data set for every single instance of a mononuclear transition metal complex, which means there's exactly one and only one transition metal. And we got about 270,000 total results. So this is great. Here's an example of that on the left. We then extracted the ligands by simply reading in the 3D coordinates and deleting the metal. Then every resulting connected component that's no longer connected must have been a ligand, because when you delete the central node, you get these disconnected subgraphs. We then encoded all of these ligands in their coordination modes by storing which bonds were deleted when we remove the metal. That tells us which atoms shared edges with that metal. Then we passed them all through a graph hashing algorithm, store only unique entries, and filter them according to key chemical filters, which are some representative ones are shown here. So first, we looked only at unique entries that gave us a little over 95,000 ligands. We looked at only the ones which you could write a valid SMILE string for, which is just a canonical representation of the connectivity of a molecule. And being able to write a valid SMILEs indicates that the connectivity is well resolved and it's a good quality crystal structure. That took out just under around 9,000 structures. Then we filter for things that are non-hemilabile, which that means that no matter what the context is, the ligand is only observed to bind to the metal in exactly one way. If you change the metal or change the environment, the bonding remains unchanged. It's uncommon that a ligand is hemilabile and that the coordination changes, but this subset, despite being small, is very chemically interesting. So we discard it for now, but we're going to revisit this assumption later in the presentation. But for now, we're only looking at things where there's exactly one right answer. We filtered for valid elements, so things like that are well represented in the data set. We have very, very rare instances of things like antimony binding to the metal, but by and large, we're interested in carbon, nitrogen, oxygen, phosphorus, sulfur, silicon, that sort of chemistry. We filtered for a valid denticity, which is the number of bonds that you form to the metal. We noticed a precipitous drop in the distribution as you look at things forming 7 or more bonds, so we just cut it off at 6, keep holding things up to 6. Finally, that brings us to a final data set of just over 70,000 unique ligands, all of which were experimentally synthesized and which we know the coordination to a transition metal. And the final thing that we do that I like to bring up here, because obviously this is a machine learning presentation, we train deep learning models to, given the ligand, predict how it binds to a metal. Rather than doing some sort of random split, we impose a similarity split based on more than fingerprints, which simply means that because chemical data is graph-based, and you can end up with highly similar graphs that are still unique because they're not completely isomorphic. It's unfair to, for example, train on this far left ligand, test on this middle one, which differs only by a single nitrogen atom, and then validate on the third. Because even though they're technically different graphs, they're all going to bond very similarly to the metal. And it's unfair to learn a representation of one and test on the other. You'll have data leakage. So what we do is we fingerprint every single ligand, we calculate its similarity to every other ligand, and ensure that things that are highly similar are bucketed together in training without tests. So this is thought to slightly decrease test set performance. So the statistics are a little bit less inflated than you would see elsewhere, but the generalizability is thought to improve. So one question.
One question, yeah. Maybe you will touch on it later. For the no valid SMILEs, so that one there is, I would assume, is a CP ring, which is super common, but you're right, the SMILEs is wrong when you read it with like RD kit or something like that. I don't know if you're gonna touch it on it later, but do you have a way of including it, or yeah, because I feel like it's a valid and pretty used ligand.
Yeah, no, that's a good question. So yeah, CP, I like to include this one because I like to get that question. The CP is a very common quintessential ligand, like for your ferrocene complexes, but technically you can't write smiles for it. It's not in the data set. And another ligand that's very common and is not in our training data is triphenylphosphine. The reason is that typically it's the phosphine that binds to the metal, but very occasionally you'll see that it's one of the phenyl rings that does haptic coordination to the metal. And because there's now 2 right answers to throw that out from our data set, these models haven't seen CP and triphenylphosphine, despite them being like the 2 most common ligands. But then once our models are fully trained and we test on them, you can give them CP and give them triphenylphosphine and they get the correct answer. So it suggests that those coordination modes are implicitly encoded by other more complicated ligands that are in the training data. So it's a nice little tool.
Cool.
Yeah, hope that answers your question. Thanks.
Yeah, there's also another question. It's how do you test if a ligand is non-hemylable?
Oh yeah, good question. So to test, I'll back up just a little bit. To test if a ligand is non-hemylabile, basically we first have this transition metal complex. When we delete the metal, we see all edges that were broken. So then what you can do is you can hash the ligand by passing it through some Westphal-Lehmann hashing test or whatever graph hashing test you prefer to use. It gives you a unique representation of the ligand without the metal. You can then add just the metal back in and hash the ligand again. And for something to be non-hemylabile, it means that there's a 1-to-1 mapping between does exactly one ligand, when you add back a metal, map to like a single coordination mode. And if you see that one dissociated ligand maps to multiple different graphs when you add the metal back in, it means it must have been bonded in multiple ways. Basically, it's this violation of a 1-to-1 map.
Just one follow-up on that. So when you add back the metal, you would relax it again, I guess, and then you will see if the density changes?
So actually, our models are all 2D. We only store the, we don't use 3D information at all. We store the 2D conductivity. And the reason is, yeah, like the vast majority of ligands have been synthesized only like a handful of times. So we don't have reliable 3D information. And we wanted these modeled because like a SMILES encodes a lot of connectivity that's relevant for organic chemistry. We wanted to see if we could get by just using 2D information to just improve the inference speed in the general, how easy these models are to use.
Sorry, just a follow-up question as well.
Yeah.
For the fingerprint, is it something that gives you like a similarity? I'm not familiar with the technique used.
Yeah, so the Morgan fingerprint, I'm not an expert in the algorithm. We used it because it's implemented in our kit, but from what I understand, basically it's a bitwise representation of the molecule. So given a molecular graph, it generates a fixed length bit vector of the presence or absence of different substructures in that graph. And that gives you typically like a length 2048 binary vector that you can then compare to any other molecule's vector using a function called the Tanimoto index. And then it just gives you a score 0 and 1.
Do you find that to work well in practice, or do you feel like it had some limitations and that you need to, at some point, like move further?
Yeah, so in general, I think Tanimoto similarity and Morgan fingerprints are widely used for organic chemistry because I think they work reasonably well. The one like big issue with them is that they're only 2D. They ignore any notion of 3D information, which for the purposes of this work was fine because we're only training 2D GNNs. But for future work, yeah, where we care about things like cis-trans symmetry or chirality, I would think a 3D-based similarity metric is essential. And there's some work in that from other groups where I think they basically represent each atom in a molecule as a Gaussian, calculate overlap of Gaussians and things like that to get similarity. But yeah, it is kind of an outstanding issue in the field.
Right, thanks.
Yeah, of course. All right, I'm going to move on to the next slide. I'm happy to keep taking any questions, but this is just basically this is how we got our data set of roughly 70,000 unique complexes to train our GNNs on. So then, before training it, we actually inspected the data set, which is an important thing to do. And we make sure that the distributions reflect what we would expect just from knowledge of organometallic chemistry. We see that when we look at the different coordinating atom elements, nitrogen was by far the most common atom that's going to coordinate to a metal, which is consistent with just textbook classical transition metal chemistry. Nitrogen likes to bond because it's not too electronegative, and it's not too electropositive. So it's bonds more favorably than carbon and oxygen, but it's also earth abundant. So it's just a commonly used word. When you look at the distribution of the number of coordinating atoms, you see there's a significant increase in bidentate ligands, which is rationalized through something called the chelate effect, which basically it says that when you have a ligand that has two separate points at which it bonds to a metal, that's called chelation, and just that ring strain induces some increased stability in the complex. And those sorts of ligands are pretty commonly used in synthetic chemistry as well. The thing that I'm going to point out here at the bottom too is the distribution of different transition metals. We can see that things like ruthenium, nickel, cobalt, and copper are pretty well represented, but things like titanium, vanadium, or zirconium are less so, which is just something to note about the Cambridge structural database, that not every element is equally represented. So then now, moving forward, we trained these 2D graph neural networks using only a SMILE string as an input, because we have a SMILEs for everything in our data set. So SMILEs encodes connectivity, but it also encodes certain other chemical information that we use for our initial representation. Key things were, so we have an initial fingerprint, including key information like the atomic number of each element, how many bonds it forms, the hybridization, standard descriptors like that are cheap to compute from a SMILEs. We update this iteratively using a directed message passing algorithm, and then end up with a learned representation, which is then passed through a feed-forward neural network. This is all standard stuff for how the majority of modern graph neural networks for chemistry work. Rather than using some fingerprint initial representation that's just passed through a feed-forward network, you use message passing to update and get a learned representation that's more expressive. We then evaluated these models first on how accurately do they predict the coordination number, which is just how many bonds does this thing form on the metal. We saw roughly 89% accuracy, so reasonably strong. The other thing to point out is that while the model is sometimes wrong, like it's maybe going to predict a bidentate ligand as actually being monodentate, it's very rare that you predict a true bidentate ligand as being like hexadentate or something. So typically, predictions are accurate, and when they're not, they're only off by 1 or 2 bonds, which is something that is likely chemically accessible, because just as you haven't seen this ligand in that coordination mode doesn't mean it's impossible, because most of these we only have one data point for. But more interesting is actually the coordinating atoms. If you want to use this to build a 3D structure of a complex, you care about not just how many bonds does the ligand form with the metal, but exactly which atoms are forming bonds. The accuracy here looks a lot better. 99% of atoms are correctly classified as 1 or 0, does it bond or does it not bond? But the more skeptical of you in the audience should probably raise some valid questions, which is this 99% accuracy is actually trivially high because the overwhelming majority of atoms are not coordinating atoms. You could predict 0 for everything and you do pretty well. So when we evaluate these models in terms of balanced accuracy instead, which weights positive and negative predictions equally well, we still get about 97%, which is still good, but it's not high enough to be, it's still a little misleading. And the reason is that, consider this ligand here on the right, where it's truly phosphorus sulfur bidentate ligand. This phosphorus atom was correctly predicted to bind to a metal, but we were wrong on the sulfur. We predicted 0.46, which rounds down to 0. So we got every single atom in the molecule right except 1, giving us a 96% overall accuracy. But we imposed a new metric, which basically means it's called molecular accuracy, which means that every single element has to be correctly classified. So even though in this molecule everything was right except the sulfur, we would call this molecular accuracy of 0. And applying this very stringent criteria across the entire data set, we get, see that there's a molecular accuracy of about, oh shoot, it's being blocked, 85% should be what it is. There we go, 85%. Yeah, and one thing that I also like to point out when giving this presentation is that while these models they're performant and achieving high accuracy, the question of like what sort of chemical heuristics, how chemical heuristics would have done typically comes up. And the heuristic that people like to use is you can just look at the heteroatoms and assume that the non-carbon atoms are going to bond to the metal. If you apply that heuristic across the entire data set, you get accuracy of about 23%. These models are significantly outperforming just back of the envelope calculations. And then now looking a little bit closer at these, there are instances where you have predictions that are high in uncertainty. And because we have 2 different models, one for the coordination number and one for the coordinating atoms, we can overwrite the more uncertain prediction to enforce chemical consistency and improve some accuracy. So I can explain this by going through a worked example. Basically, we first separately predict the coordination number of coordinating atoms. In this case, as I showed you before, we predicted that only one atom is going to coordinate. It's just as phosphorus. If the predictions agree, we do nothing. However, the coordination number model confidently predicted that this is going to be a bidentate ligand, but our coordinating atoms model only picked up on phosphorus. So obviously 2 is not equal to 1. These two predictions are physically inconsistent. In the case of physical inconsistency, we overwrite the predictions of the less confident model to be consistent with a more confident model, where confidence is just measured by what we define uncertainty as the deviation from, like a true prediction of 0 or 1. So if we predicted 0.79, that is 0.21 uncertainty because it's 0.21 away from a true confident prediction of 1. In this case, the uncertainty is 0.46 because that's the largest distance from 0 to 1. The coordinating atoms model is more uncertain. We pick the next most confidently predicted atom and return it. And now we correctly return the coordination mode that's observed experimentally. So this little synergistic algorithm is straightforward to implement and straightforward to execute across the entire data set. It's very cheap, but doing so increases accuracy of both models to roughly around 90%. And then finally, I like to close this section, which is showing a couple of different examples that these models generalize the pretty diverse coordination chemistry. So zooming in on this one complex here on the left, we can play a little game. Happy to take guesses if anyone thinks they know how it's going to coordinate to a metal. But it ends up being a tridentate pincer ligand, where this nitrogen, second nitrogen, and sulfur atom come in and coordinate. So our model is able to distinguish between coordinating and non-coordinating heteroatoms. It doesn't see the oxygen and see the nitrogen and just simply count all 5 of them, return 5. Looking at this complex here on the right, it's truly a pentadectic complex, and our model is able to capture these high density binding modes that are less represented in the training data. Remember, the majority of our training data was mono, bi, or tridentate, and the model was able to perform well on these higher density modes. Look at this ligand here on the right. You could easily jump to the nitrogen or either of the oxygens, but it actually ends up being this haptic coordination due to delocalized electrons and aromatic rings, which the model also accurately predicts. And finally, my favorite example is we see these very common coordinating atoms of phosphorus and sulfur, but rather than those, it's actually an anionic silicon coordinating atom in this case, which is roughly 1% of the data set, but the model is still able to identify these coordination modes. Yes.
I have a question. Do you expect that like the missing percentage of accuracy in the model could be because like 2D information is not enough to correctly understand how the metal would bond?
Yeah, the absence of 3D information could be part of the issue. I think that another reason that there's some inherent data contamination in such data sets, because if you have a ligand that's been synthesized 100 times, and we know that it only ever binds in a single coordination mode, like just for example, take a phosphine ligand, you only ever see that it binds with the phosphorus. But if you have a ligand that's only been synthesized once, it's hard to say whether or not another binding mode is not feasible just because it's never been observed, because we've only seen the ligand one time. And that's why I like to point out that these predictions are usually only off by a single coordination mode, because it kind of suggests that even though these things they're not what was observed experimentally, we've only synthesized this ligand one time, so it could be a valid coordination mode. The inclusion of 3D information would likely help, but it would be challenging to separate the effect of just like methyl group rotations or like the inherent floppiness of these like large systems.
Thanks.
Yeah, sure. Great. Now I'll move on to talking about the project that you guys actually invited me here to speak about, which is acknowledging that sometimes there's more than one right answer for how does a ligand bind to a metal, and how can we extend our approach to handle these dynamic coordination modes. Great. So the term I'm going to be using a lot here is hemilabile and hemilability, and that just simply refers to a ligand with multiple valid coordination modes, and it introduces unique challenges to our models. So An example here, pretty much the quintessential example of a hemilabile ligand is this one called terpyridine, which goes back and forth between a tridentate and a bidentate coordination mode. And this dynamic exchange in how many atoms are bound to the metal is known experimentally to an enhanced rate by orders of magnitude, and it's been observed for decades. So people really care about these types of ligands, especially in catalysis, because the idea is that when you have all three atoms bound to the metal, all the metal's active sites are covered. You can have a substrate come in, and then one of the ligands dissociates. The substrate is able to undergo an exchange due to the metal, and then is rapidly ejected by the return to this high coordination mode. That's how people rationalize the increase in turnover frequency due to the use of these ligands. However, this one is like a very commonly known hemilabile ligand, but looking at these two examples on the right, it's pretty much the same ligand twice, these two amine systems, where they differ only by the presence of one methyl group here versus one hydrogen group here. Both of them have been synthesized dozens of times with about a dozen different transition metals, but one of them is known experimentally to be hemilabile, and the other one has never been observed as being hemilabile. So chemical heuristics struggle to predict whether or not a ligand is hemilabile, let alone what the different coordination modes are. So in previous work done by then a postdoc in the group, Dr. Ilya Kevlishvili, and now a professor at Baylor University, he trained models that showed that if you know what the coordination modes are of the ligand, at least one of the coordination modes, you can confidently and with high accuracy predict whether or not it's going to be hemilabile. And the main contribution of this work is that he curated some pretty large data sets, which were labeled as hemilabile or non-hemilabile using a semi-supervised learning approach, which started off with ligands he was very confident about, and then spread the labels to data sets he was less certain about, and was able to iteratively define these sets of highly confident labeled ligands. However, our work, which we showed recently, we can confidently predict the coordination, so we need no information of it, but we assume implicitly that all ligands are not hemilabile. So the natural question is, can we marry these two approaches, and can we take the GNNs I showed you previously and extend them to the case of hemilability? And before I show you the initial results on that, I'll show you just what we define by hemilabile. So there's 4 exhaustive and mutually exclusive classes of how a ligand can be hemilabile. The first one I already showed you, it's represented by terpyridine. It's basically that the 2 coordination modes are subsets of one another. These 2 atoms that are bound here are a subset of these 3 atoms, but there's a net change in the coordination mode. We go from 3 to 2. Another possibility is that the atoms are not subsets. So we start with this phosphorus and end up with these 2 nitrogens, but there is still a net change of the coordination number. So it's high density to low density transition. Class 3 is what we call overlapping sets, but the coordination number is constant. So we have an example here, this fused ring system, where it's either these 2 nitrogens or these 2 nitrogens, which are similar but not identical due to symmetry. But the coordination number overall, no matter what, is net unchanged. It's 2 in both contexts. And finally, very common ligand thiocyanate, this behavior is known. The coordinating atoms are either nitrogen or sulfur. There are non-overlapping sets. The coordination number is constant. So yeah, if you go through all the ligands and go through all the possibilities, these types of hemilability are really the only 4 you can get. These are the 4 canonical classes. Class 1 is by and large the most common. It's about 80% of the data. And classes 2, 3, and 4 are less common, but still chemically relevant modes. So the question now is, can we take the GNNs that I showed you earlier in this presentation, and can we out of the box train them on just like fine tune them on hemilability? And the answer is no. So the initial approach that we used, just leveraging it immediately to hemilability, didn't work very well, likely due to the fact that our data set here is only about 7,000 structures, whereas in the previous project it was 70,000. So an order of magnitude difference. We see accuracy and AUC metrics that really aren't that great. But we can do something that's a little challenging for me, and which is to think like a chemist and apply some chemical intuition, a little bit of math, and come up with a new machine learning strategy to improve this accuracy. So we know that hemilabile ligands, by definition, lack a well-defined coordination mode, because that's what makes them hemilabile. There's at least 2 right answers. So therefore, we expect that our previous models, which have not seen such ligands, will be more uncertain. They'll have a higher prediction uncertainty. So we can just take that, we can run these ligands through those other models and run inference and collect all the uncertainties, and use those as features for a new model. So we can featureize this binary classifier with the uncertainty of the other models. We can also note that hemulability is related to coordination, like the idea that a ligand can change between two different binding modes is inherently linked to what those binding modes are. So we expect that the Lund representations of these problems will be related, so we can pre-train on our much larger coordination data set of 70,000 structures. In doing that, we see that performance improves quite a bit. Shown here in blue is the fine-tuned model, where we get AUC metrics up to 0.92. And we also should note that this increased performance outperforms a lot of other methods that we tried, including quantum mechanics descriptors and just descriptors based on the molecular graph. So the large data set of ligands that we pre-trained on at the similar latent spaces really helped in the generalizability. Now I can show a bit on how this fine-tuned model works and that it detects chemical nuances of hemulability. So first, here's the prediction that was incorrect before we fine-tuned, but was corrected. So that's this phosphorus ligand, that's the only coordination mode that it ever observes. It's only going to be the phosphorus that binds to the metal. But our non-fine-tuned model was very confident that this is a hemulabile ligand. But once we ran it through fine-tuning, the improved model was able to correctly assess that this is not a hemulabile ligand. Its prediction is 0.18, which rounds down to 0. We have another example here where this ligand truly is hemulabile. It's kind of challenging to look at because it is highly symmetric, but it's these two nitrogen atoms that can coordinate, both of which are distinct. The default model is very confident that this is not going to be hemulabile, but the fine-tuned model got a prediction of 0.55, which rounds up to 1, which is more correct, more accurate. The story is not perfect. There are still examples of ligands that are incorrectly classified, even after fine-tuning. An example was shown here where the true answer is 0. Our prediction goes from 0.84 down to 0.6 upon fine-tuning, so it's still incorrect. We see that the uncertainty is much higher, which kind of makes sense qualitatively because this ligand looks a lot like terpyridine, which is the classic hemulabile ligand, but it's not hemulabile, likely due to the presence of these CO groups, which are kind of rigid and prevent the rotation. So the model is expressing this uncertainty. However, I've just shown you 3 examples where the fine-tuned model was often correct, but just more uncertain. So one thing I want to demonstrate is that we did not just make things more uncertain. This increased uncertainty across the board is pretty much only observed in the predictions that ended up being wrong, while we look at predictions that ended up being correct, and our fine-tuned model exhibits similar prediction certainties than the non-fine-tuned, the default model, suggesting that negative transfer is not really occurring. And then, so I've shown you 3 different models thus far. One to predict the coordination number, one to predict the coordinating atoms, and finally now this binary classifier that yes or no, is this ligand going to be hemulabile? The dream would be to use all 3 of them together to predict not only is this ligand going to be hemulabile, but what are the different coordination modes that it can possibly exhibit, and can we rank these coordination modes? So to do that, we define some ensemble learning algorithm, which enables an end-to-end workflow for this prediction. So we start just with a smile string. We run inference with our 2 initial models that I showed you for coordination number and coordinating atoms. We predict this is a tridentate ligand with nitrogen, oxygen, and sulfur coordinating these 3. We then run it to the 3rd model, the hemulabile classifier, using the uncertainties from these 2 as features with a 30. We predict with 97% confidence that it is going to be hemulabile. If we did not, then we would simply be done. We would return this predicted coordination mode and we would move on with the day and build a complex according to it. But because we did predict that it was hemulabile, we can enumerate all the different possible combinations using this enumeration algorithm, which basically iterates through every possible coordination number defined by the model, so between 1 and 6, and looks at every subset of heavy atoms of size equal to that coordination number, and ranks all these sets by the mean probability of the atoms. Iterating through, it's a combinatorial algorithm, so it doesn't scale well to very large ligands, but because it worked well on the entire data set because none of our ligands are that large. Using this algorithm, it suggests that this sulfur atom, it's possible for that one to dissociate, and that this bidentate mode is another experimentally plausible coordination mode. And this actually matches up with what was observed experimentally in the CSU. This ligand has been seen to be tridentate and bidentate with those 2 different coordination modes. then finally, we wanted to actually validate some of these predictions in quantum mechanical calculations. So we queried the CSV once again for all transition metal complexes with identical metals and identical ligands with distinct conductivity. So exactly one ligand is bound in a different manner between the two TMCs. And this is not a very common occurrence. We only got 77 pairs of these. An example is here, this lead-ruthenium complex, which is sometimes bidentate and is sometimes tridentate with this labile oxygen coming on and off. But otherwise, the ligand, the whole complex is unchanged. We performed DFT calculations on both of these at the PB0, P3BJ level of theory with a small basis set and calculated the energies of the larger triple zeta basis set. Found that the difference in energy between these two structures was 10 kcal/mol. When we did this with all 77 pairs, we saw that the average difference in energies was about 10.4 kcal/mol. So a representative example is the one I'm showing here. Using this 10 kcal/mol baseline, we wanted to evaluate some of the ligands that we predicted are or are not hemilabile and see what their differences in coordination energy look like. And to do this is challenging because we only have the ligands. They were synthesized in different TMC contexts, so it's unfair to compare a different metal with different other spectator ligands. So what we did is we defined these, what we first randomly chose ligands that we did not know whether or not they were hemilabile. We didn't have enough data to say for sure. But our model predicted that 25 of them were hemilabile, 20 were not, and they predicted confidently. An example is shown here, one that we really thought was hemilabile. We built these zinc chloride scaffolds. We attached the ligand to these zinc chloride scaffolds, and we chose zinc chloride because it's a common motif in TMCs. It's simple, and zinc is likely to be closed shell, so we wouldn't have to worry as much with the exotic spin states. We calculated the difference in energy between these two, saw that it was about 7.2 kcal/mol. When we do it across all 25, we get 12.5 kcal/mol on average. And finally, we repeated this process with the ligands that we really confidently did not think were hemilabile by forcing our algorithm to return another coordination mode anyway, even though it thinks it's too low probability, and building the complex in these two modes. So here we see we go back and forth between this haptic carbon atom binding to the zinc, which is just qualitatively, you can look at it and see that it's unlikely. The energetics line up as well. The difference in energy here was 50 kcal/mol, and across the whole data set of these 20 non-hemilabile ligands predicted, that was about 30 kcal/mol. So the distributions, these examples look good, but also the distributions, we see that looking at just the CSV structures, the majority of them have energy difference of about 10 kcal/mol, and it stops a little bit further out here. We look at in green predicted hemilabile and red predicted non-hemilabile. The green predictions line up pretty well with the gray experimental observed distribution. Not just in terms of the mean, which is 10.4 versus 12.5, or 27.8 for the red distribution, but also in terms of like the cumulative distribution function. Similar metrics are observed if you compare the distributions using t-tests or Wasserstein distances, which basically shows that while this is a imperfect assessment, like using just DFT calculations, you can't really assess all the different energetic contributions from a ligand flopping around in solution. But as a first order approximation, the energetic agreement between experimentally observed hemilabile ligands and predicted hemilabile ligands is pretty strong, suggesting that our models predict reasonable coordination modes. And then finally, putting all this together in an end-to-end fashion, it's more user-friendly. We integrated these models into one open source package called Pidentate and put it inside Metal-Ligand, which is our group open source software for building 3D structures of transition metal complexes. And our workflows enable the high throughput screening of very large ligand databases. So start with just a SMILES input, run it through Pidentate and get a prediction of which ligands are going to coordinate to the metal, and then very easily build 3D structures of these using Metal-Simplify. And this, the models that I showed here were trained over the course of this work, but the integration with Metal-Simplify was done by 2 PhD students in the group, Roland and Gigi. And yeah, you can then screen very large ligand libraries and run these through physical simulations. The source code, models, and tutorials are all hosted on GitHub along with the web GUI for just making very easy one-off predictions. And yeah, the GitHubs are shown here. For the very easy prediction of coordination modes and generation of structures. We validated it in the Molt Simplified 2.0 paper by running this through a bunch of ligands to produce iridium complexes that matched up well with the known experimental structure of these iridium complexes. But yeah, it should enable the accurate screening of arbitrarily large data sets, and then building 3D complexes with them and running them through your favorite flavor of electronic structure theory. Cool. Happy to take any questions now if there are any, but if not, I can move on to the final portion of the paper, which is extensions to generative models. Right. So yeah, basically, the motivating story of this portion of the presentation is that generative models for organic chemistry can be fine-tuned to organometallics. So I'll be showing 2 example projects here that I contributed to, but were led by collaborators. So the first one is this robust TS generation project led by Samir, wonderful PhD student at the University of Stuttgart. We found that out-of-the-box methods to predict transition states for organic reactions do not generalize to inorganic reactions. So taking a little bit of a step back, the reason we care about transition states is that we want to do kinetics with these things. We want to be able to study, computationally study a reaction underneath the transition state to get a reasonable estimate of the rate. The transition states are very hard to optimize to because they're represented by a first order saddle point, the potential energy surface. The optimization is very expensive, very challenging, and very sensitive to initialization. So it's error prone and time consuming. So people over the years turned to machine learning to try and predict these transition states. State-of-the-art models use diffusion or flow matching algorithms, which is basically take your reactant and product and interpolate and find a good guess for the transition state structure. But when we took these state-of-the-art models and tried to generalize them to additive distribution chemistry, we didn't think they would work. But in order to test this, we had to use data augmentation. So we took the transition 1x data set of small organic reactions, systematically replaced some elements with their same elements in a different row of the periodic table. So oxygen became sulfur sometimes, nitrogen became phosphorus, carbon became silicon, and we redid the transition state calculation. We also added some very active distribution chemistry using transition metals. And in order to do this, we took every organic molecule in the transition 1x data set, predicted its coordination to a transition metal using the identity models, and then simply docked the TMC next to the ligand and had it represent a catalytic reaction and redid all the optimizations along the reaction coordinate. So this result then data set is a lot larger. We have tens of thousands of transition metal catalyzed reactions now. The existing models did not generalize, so we went from very high state-of-the-art performance with small RMSDs between predicted and true transition states, small energy differences, to see here the carbon-carbon bond distance that's predicted, which is a dashed line, matches very well with the true distance, which is a solid line. When you start looking at additive distribution chemistry, the model fails terribly because it has no prior for what a carbon-silicon bond or a carbon-germanium bond looks like. And the delta E goes from on the order of 10 kcal per mole for in distribution chemistry to hundreds of thousands for out of distribution chemistry. So some fine-tuning and data augmentation is necessary. When you take these same models, when you fine-tune them on some of the out of distribution chemistry, we find that the pre-training achieves state-of-the-art performance on unseen TMCs. So down to 0.1 RMSD and 0.1 on the order of 1 to 10 kcal per mole difference on this transition metal catalyzed reaction chemistry. Shifting gears a little bit, the final project that I wanted to show is something called TMC Llama, which took the Llama large language model trained by Facebook and fine-tuned it on transition metal chemistry. And the idea here was that rather than looking through finite but large data sets of organic ligands, you can train large language models to know what organometallic chemistry looks like and to propose and generate new transition metal complexes. But of course, as we know, LLMs are sensitive to hallucination. We wanted to actually validate the chemical plausibility of these generated TMCs. So to do that, we took all the complexes generated by this TMC Llama model and screened the chemical validity with a bidentate surrogate, which means took the proposed TMC, deleted the metal, took all the ligands, and predicted whether or not the ligands should bind in the same way the LLM said they were going to bind. And we saw, on average, that this TMC llama model got between 70 and 80% validity, depending on exactly what model configuration was used. And previous generative models existing in the literature scored only about 40% accuracy. So just showing here a couple representative examples, we have these asymmetric palladium complexes or platinum complexes, this linear silver complex with the non-heterocyclic carbene ligands, which are pretty common. And finally, this, again, a palladium complex. And these are just representative examples of TMCs that were generated by this large language model. But all of these TMCs are out of distribution of the CSD because they're not anywhere in the CSD. And the coordination modes that were predicted by the LLM matched up with what was predicted by identity. Great. So that does bring me to the end of the research portion of this presentation. What I want to talk to you all about, I'll just close briefly with a summary where we curated very large data sets of over 70,000 experimentally observed Metal-Ligand coordination modes. We leveraged GNNs and Ensemble learning to effectively capture organometallic bonding. We put together these open source workflows for the high throughput TMC screening. We integrated them with generative models for data augmentation and assessing the validity of complex. Future work that we're engaged with is an integrated 2D to 3D to electronic structure prediction workflow. And we continue development of more generative models for the guided exploration of capital space. And all the software that I talked about is available on the open source GitHubs. And yeah, with that, I especially want to thank everyone in the group who contributed to this work, certainly Roland, Aaron, Ilya, and Professor Kulik, and certainly our collaborators, Samir and W. and Liu, whole Kulik Group. And yeah, thank you all of you for having me and for your attention throughout. Happy to take any more questions.
Cool. Thank you so much. There's one question in the chat.
Yeah.
Do you confront your predictions to laboratory tests? Like going even beyond, is there a cross-validation on lab fabricated samples like 10, 100 based on potential high throughput experimentation?
Yeah, so far, I guess, assuming that you're referring to the graph neural network work, every single complex that was in our training, validation, or test data was an experimentally synthesized transition metal complex. So everything in there in our data set we mined from experimental repositories. Someone had already synthesized it, and we trained our model to reproduce this experimental structure. In terms of the out of distribution, like the large language models, that work is still in progress and like under review. But no, they're both computational groups, so I don't think any of it has been explicitly experimentally characterized. But I'm sure that's an exciting direction for future work. The point of using the identitate models as surrogates is that even though they're still graph neural networks, they were trained exclusively on experimental data. So the idea was that they should encode like a good prior of whether or not this complex is in a synthetically realistic coordination mode.
I have one question. So the CDS data, that's on crystals, right? So like all these denticities and ligands and so on, this is in crystal structure, but not necessarily in like single molecule realm. Is that correct?
Yeah, that's correct. So it's like it's not in solution, if that's what you're asking. And it's not like characterized through any sort of like chromatography or mass spec. Yeah, it's crystal structures which are crystallized sometimes in a solid heat present, and then passed through like X-ray diffraction to determine the positions of the heavy atoms. And the reason for this is that it's the only large open source data set for training such models. But yeah, the implicit assumption is that when you go away from the crystal environment, things are gonna change a little bit. And we're assuming that the change is not going to be dramatic. But I think the theme of the majority of this work is because the transition metal complex space is orders of magnitude larger than the organic chemistry space, put together the most accurate high throughput methods that we can, identify the most promising and realistic candidates that we can, and then using these candidates, like apply the full force of quantum mechanics to them to simulate them as realistically as we can, and only then invest the experimental time. But yeah, I agree with you that there are limitations in the crystal environment assumption.
Okay, thanks. There's another question. Are you working on developing a model towards predicting features related to the application? So like catalytic activity, depending on the metal ligands or some others?
Yeah, that's a great question. I didn't talk about it today because I didn't have time, but actually a previous paper from our group, I think a year or two ago at this point, published in Faraday Discussions, uses natural language processing to do exactly that. So it takes the TMQM dataset, which is a data set of about 80,000 transition metal complexes, which were experimentally synthesized from the CSD. And because they were synthesized and deposited, they all have papers and manuscripts associated with them. So we developed a workflow to mine these papers. I guess they don't all have papers, but the overwhelming majority have papers. We mined them all, mapped them back to the structure that they are associated with, and used a fine-tuned, I think it was a per topic transformer model to do topic modeling, and then found that we curated 4 large data sets, one which we call the TM-CAT for catalytically relevant, one is the TM-BIO for biologically relevant, and we had a TM-PHOTO for photochemically relevant, and the TM-SCO for spin crossover complexes. Yeah, these data sets vary in size. The TM-CAT data set is about 50,000 complexes, if I'm not mistaken. TM-SCO, I think, is only 2,000. So they vary dramatically based on how representative that application is in the data set. But yeah, I think that's an exciting avenue. It's becoming harder as journals make it harder to mine their papers off the internet with the advent of like LLMs. But yeah, it's an interesting area.
Yeah, I have one last question on the transition states. So you extended the data set by just replacing, and I think like, for example, OMOL also did the same, kind of like just replace atoms and assume that would work. You just did it in 2D, right? It's not like you did it in 3D, then minimize its energy and see if it actually changes structure.
No, so these are 3D. Yeah, the initial work that I showed you was all 2D. The moment we switched to quantum mechanical calculations is when they became 3D structures. So when I showed you the energetic assessment at the end of,
it's true. Yes.
Yeah. So this analysis is all 3D, of course, because we had to run DFT on them. And then moving forward just a little bit, actually, I can just move to the backup slides. This was all. So this data augmentation process. This is all 3D. So transition 1X includes 3D structures of the reactant, product, and transition state for on the order of 10,000 reactions. We randomly swapped some with different elements in the same row of the periodic table, or excuse me, the same column of the periodic table, and re-optimized them. So we redid the transition state search, we redid the reactant and product type optimization, we redid the IRC to converge everything, to converge the reaction manifold was unchanged. And if anything deviated by an RMSD above a threshold, we threw that reaction out. So what I'm showing you is only the things where we confirmed the chemistry was unchanged.
Okay, that's super interesting.
Okay.
All right, I don't think there are more questions. Thank you so much again for presenting. Super
Thanks for having me.
interesting. Yes, we'll upload the recording, and yeah, again, thank you so much.
Thank you.
Thanks. Yeah, I appreciate your time. Have a nice day.
Have a good day. See you.